So, welcome to my CCENT training material. This is Chapter 8. This chapter is dealing primarily with just IP addressing. In this chapter, we're looking at IPv4, IPv6, and connectivity verification for both 4 and 6 IP addressing. So the main objectives are, once you're completed with this chapter, you'd have basic understanding of IPv4, IPv6, kind of what they do. So let's start with IPv4 and binary notation. So we deal with everything in base 10 numbering system. So 10, 100, 1, 10, 100, 1,000, 10,000, and so forth. So if we're doing some type of positional methodology, we can actually look at where our positions are. For example, if we look at 1, 9, and 2, let me grab my pen real quick. This is the 1 spot. That's the 10 spot, and that's the 100 spot. That's why we're able to get things like, in the 100 spot, it's worth 100. In the 10 spot, it's worth 10. In the 1 spot, it's worth 1. So we get 1 times the value of the position. So there's 1, 100. There are 9, 10, and there are 2 1 spots. That's how we get 100 plus 90 plus 2. It's kind of important to get that type of positional method down because when we move to binary conversions, that kind of helps a lot. Here we have a binary, and you're going to notice, first of all, its positional method, it starts with 1, and it just doubles. In this numbering system, we can either have a 0 or a 1, binary, bi. So this will either be 1 or 0. This area will be 1 or 0. Because our number is 110000000, basically we add just where the ones are at. And add them up. 128 plus 64 equals 192. If we take this 168, we do the same thing. We add the 128. We do not add the 64. We add the 32. We do not add the 16. We add the 8. And when we get all of that together, it's 168. It's important to realize that an IPv4 address is binary. Its base system is binary. It will be presented in dotted decimal form, meaning here is a group of 8 bits, a group of 8 bits, a group of 8 bits, and a group of 8 bits, all separated by groups of 8 by a period. Dotted decimal. 8 bits plus 8 bits plus 8 bits plus 8 bits equals 32 bits long. An IPv4 address will always be 32 bits, and it will always be 4 groups of 8. So converting our binary to decimal, again, same thing. If you look at the chart, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and so forth and so forth. How I tell most people is start the number 1 and keep doubling it. That's how we can always build this chart. So let's get some practice done. If we looked at the previous practice and add where the ones are at, it should equal 176 and 255. If we're looking at the larger chart, here it is. Each octet will be groups of 8 bits, normally starting with 1 and doubling all the way to 128, and we add just where the ones are at. And that is how we get our dotted decimal address. So how do we take a decimal and convert it back to binary? Basically what I do is, can 128 go into 168? Yes or no? If it does, minus 128, put a 1 there, and just keep working. The remainder is 40. Does 64 go into 40? No, it does not. Put a 0. Does 32 go into 40? Sure it does. The remainder of 8. 16 go into 8? No. Does 8 go into 8? Yes, it does. Remainder of 0. And they are all zeros. And again, the flowchart does the same thing. Again, each of these groups of 8 bits will be 8 bits. That's an important concept. They're groups of 8 bits. Always. We actually call each group of 8 octets. So we have the first octet, the second octet, the third octet, the fourth octet. First, second, third, fourth. So what's the purpose of our subnet masks? Essentially, they divide us into two functions. One part will be the network portion. One part will be the host portion. Essentially, what can we and what can we not play with? So let's look at some common numbers. So 255, 254, 252, and you notice to go from 255 to 254, we're just removing 1 from the 1 spot, and so forth and so forth. So these are all valid subnets because you're going to notice there's groups of 1s all the way down. There will never be a subnet where it'll be 1, 1, 0, 1, 1. They will always be all 1s next to one another. Always. So let's look at some of the prefix. If we are looking at a /24, basically what that means is there are 24 1s and 8 zeros. So essentially, if you just start drawing 1s, draw 24 of them, and then you do the remainder of the 32 zeros, you will get the appropriate subnet mask. So here they're going to ask you things like the significant that are borrowed and the first and last and broadcast address. I always hate these because they never give you enough detailed information to figure out how to do this. So basically we're going to look at how many remaining zeros there are. If it's a /24, we know an IPv address is 32 bits, so that means 8 zeros are remaining. 2 to the power of 8, we subtract 2, that gives us 254 hosts. That means our usable will be between 1 and 254. Why subtract 2? Because we're going to use 0 and 255 for our equipment, meaning they're not usable. So if we have a /25, 32 minus our 25 is going to be 7. 2 to the power of 7 is 128, but we're minusing 2, so we get 126. Why are we minusing 2? Again, the 0 and 127. That's why we have to minus the 2. So we can use everything between 1 and 126. If we do a /26, again, 32 minus 26, remainder of 6. 2 to the power of 6 is 64. 64 minus 2 gives us 62 hosts. And that's how we build off this chart. 27, 28, 29, 30, and so forth and so forth. So what does that mean by the network and host portions? So the network portion is essentially the area that we're going to lock in. So the /24 locks in the first 3 octets, meaning they won't change, meaning the host portion will change. So with this /24, basically that gives us the ability to manipulate the entire 4th octet. 0 and 255 will be set aside, but anything between 1 and 254 will be fair game. Just like we've seen in the previous slides how we did those calculations. 2 to the power of 8 minus 2, because again, IPv4 address is 32 bits. If we minus 4, we have 8 remaining zeros. 2 to the power of 8 minus 2 is our usable, which is 254. 255 and 0 are already preset aside for our network ID and broadcast. And that 254 is going to be the last usable address that we can use. So, in the Cisco environment, we have this thing called ANDing. And I hate ANDing, but our book discusses it, so we talk about it regardless. So the way ANDing works is we compare the IP and subnet mask, and if it's a 1 and 1, our network address will be the corresponding. So 1 and 1, it will equal 1. 1 and 1 will equal 1. 0 and 1 will equal 0. So here's our flow chart. When any time we're looking at an IP address and a subnet, and we're comparing the same bit position, 1 and 1 will equal to 1. 1 and 0 equal to 0. 0 and 1 equals to 0. 0 and 0 equal to 0. That's how we get our ANDing taken care of. So how do we assign a static IP address for a host? You're looking at the network adapter settings, and you're looking at the IPv4 properties. That will give us, or at least allow us the ability to manually assign an IP, a subnet, and default gateway. If you wanted to automatically assign or obtain an address, we're checking right there. But that's also assuming we have an IPv4 DHCP server running to get us the appropriate address information. We can also look at the command line. So if we did happen to choose the obtain automatically, we can first of all recognize there has to be DHCP running for us to have an address. Assuming there is DHCP address, or there is a DHCP server handing us an address, we'll go to our command prompt, type ipconfig, and it again will show us our IP, subnet, and default gateway. So within our IPv4, we have 3 major types of transmission. We have unicast, multicast, and broadcast. Unicast is one device going to one device. We have broadcast, and that's one device going to all other devices. And how that will do it is, it will look at the broadcast for that network. So again, that /24, it's going to look at 172.16.4.255, because here is the network portion. The 0 is the host portion. The last possible host for the broadcast will be 255. The 255 will be sent to all of the computers. That's what a broadcast does. Multicast is the process of sending packets from one to a select group of addresses. Normally we're dealing with a 224.00x-ish. That way it will be a specialized multicast address. Other link local addresses could be anything in the 24.000 range to 24.00255. If we're looking at global scoped addresses, it's 24.010 through 238.255.255.255. 224.011 has been reserved for the NTP protocol. Lots of nice little detailed information in this chapter. Okay, so when we talk about addressing, we also have to talk about things like public and private IP addresses. A private address block, if we are assuming that we're doing Class A, Class B, Class C, we could be looking at a private address block for Class A as anything in the 10,000 range through 10,255,255,255. That's going to be basically a 10 network with a /8. Other private address blocks, like a Class B, is going to be anything between 172.16.00 through 172.31.255.255. Again, that's going to be in the Class B range, assuming we're using classes. That will be a 172.16.00/12. Lastly, if we're using a Class C address, we could be looking at a 192.168.00 through 192.168.255.255. Notice with this, only the first two octets are locked in, so it's a /16. Meaning, as long as it starts with the 192.168, the third and fourth octet, it doesn't matter. Because these are private addresses, they are not globally routable, and this is intended for internal use only. Other special IPv4 addresses are again our network and broadcast addresses at the beginning that we don't get to use. We have a loopback address, basically anything in 127.0.0.0 through 127.255.255.255. Those are all loopback addresses. Specifically, we use 127.0.0.1, but it doesn't have to be. If we cannot access a DHCP server, we're getting a link local address or an automatically private IP address, APIPA, and that's any address that starts with 169.254.00 through 19 between that and 169.254.255.255. Again, this is an automatic link local address, and again, not globally routable. We have a testnet address, which is set aside for teaching and learning purposes, and that's going to be anything in the 192.0.20 range through 192.0.255. And then lastly, we have the experimental addresses, which is anything above 240.0.0.0 and the remaining addresses. So legacy classful addresses, again, Class A, Class B, Class C. We already talked about the private address portions, and we didn't really talk about the actual what numbers classify A, what classify B, what classify C. So if we were looking at between 1 and 127, the first octet, that's Class A. If we're looking at 128 through 191, that's Class B. Again, this is going to be in the first octet. Anything in the 192 through 224, those are all Class C addresses. But we moved away from classful addressing, and we got this new thing called classless. And formal name for classless happens to be the classless interdomain routing, pronounced CIDR. This created a new set of standards that allow service providers to allocate IPv addresses based off of a different bit boundary, meaning the subnet mask could vary. Next general question, who assigns IP addresses? It all depends on the region that you live in. ARIN for North America, RIPE for North Asia and part of Europe, AFRINIC for Africa, APNIC for the South Pacific. We have LAC, NIC for Latin America, and so forth. So there's a hierarchy. Normally, the Tier 1 providers will get the majority of the addresses. Then they subnet them, and they resell them to Tier 2s. Tier 2s will buy them in large blocks and then, again, sell them to Tier 3s. We have the major ISPs as Tier 1s. To access the internet, we're looking at going through our different tier structure back to our Tier 1 person. Realistically, most people have access to a Tier 3 ISP. So that's a nice basic overview of IPv version 4. Now let's go ahead and hop over to IPv version 6. First of all, IPv6 is a successor to IPv4. With the depletion of IPv4 addresses, that's been a huge push to IPv6. We're looking at running completely out of IPv4 addresses between 2015 and 2020. With the increasing popularity of the internet, our limited address space, as well as issues with NAT, is helping push IPv6. IPv4 with 32-bit address scheme, we're looking at roughly 4 billion addresses. But with IPv6, we have 128-bit address space, meaning it's 340 undecillion addresses, which is a huge number. IPv6 and IPv4 can coexist. Normally this is done through some type of dual stack because these are different address schemes. So IPv4 is not going to interact with IPv6. IPv6 won't interact with IPv4. Dual stacks allow IPv4 and IPv6 to coexist on the same network simultaneously. We could also have things like tunneling, and that's where we have an IPv6 only network tunneled through an IPv4 network. We have translation or some type of NAT 64-bit router, and that's where we can actually translate between IPv4 and IPv6, and the translation will be, again, allowing to go from IPv4 to IPv6 back and forth. IPv6 is all in hexadecimal, base 16. So we want to represent every possible number with a single character. That's why we get 0 through F. 0 through 9, single characters. We have A represents 10, B 11, C 12, D 13, E 14, F 15. And so forth. If we want to look at 2 hexadecimal numbers, same thing. Each hexadecimal number in binary is a group of 4 bits, always. A single hexadecimal is always 4 binary bits. So, IPv6 address representations. You're going to notice there are 1, 2, 3, 4, 5, 6, 7, 8 groups of 4 hexadecimal numbers. So each group, if each number is representing 4 bits, there's 16 bits or 4 hexadecimal bit groups in each groupings. There's 8 groupings total. So I've heard a lot of people say hextet. Some official, some no. And again, each hextet can go between zeros and all Fs. But remember, each number, each space for a hexadecimal number is 4 binary bits. So we have some rules with IPv6 that we need to know. One of the first rules is the leading zeros in any 16-bit section can be omitted. So with our address, we can actually omit these zeros, not the trailing, only the beginning ones. And you're going to see, you may have a group of zeros. You can represent a group of zeros with a colon, or double colon more specifically. but you can only use the double colon once because you have to be able to expand this back out. So if you did it twice, the addresses could change. That's why we can only do it once. So here's an example. If we drop the leading zeros, if we did a double colon here or a double colon there, doesn't matter which one we do it, it's just we can only use a double colon once. So our prefix length, just like with our subnetting, here we have two broken prefixes, 164 and the second one also 64. So this is split right down the middle. That's been very common. IPv6 address come in unicast, multicast, and anycast. IPv6 does not have broadcast anymore. Unicast, same as with IPv4, it's 1-to-1. An IPv6 unicast address could be a global unicast address, link local, a loopback, which is very similar to our loopback addresses, 127.0.0.1. We have unspecified addresses, or we have unique local addresses. These are all examples of unicast addresses. So we also have a global unicast and a link local, which we've already discussed. Again, global unicasts, those are similar to IPv4. IPv4's public addresses. They're globally unique, and they are allowed on the internet. Link local means it stays on the link, stays on the LAN, and it's not routable to different networks. Loopback, again, that's very similar to our loopback with IPv4, that's the 127.0.0.1. Unspecified addresses, that's going to be all zeros. Unique local addresses, these are going to be private, similar to IPv4 private addresses. Embedded IPv4 addresses, this is more of an advanced topic, but this is the transition from 4 to 6. So IPv6 link local unicast addresses, we could actually have more than one IPv6 address because you're going to have a link local assigned regardless. Your link local will always begin with this FE80, and the remaining 64 bits will be based off of your interface. Other link local unicast addresses, which again very similar. You'll notice these are link local. They use the FE80, meaning they will not be allowed to leave this network, but this will allow for communication on the local network. So structures for our global unicast address, again, these are equivalent to public IPv4 addresses, and that is ICANN can allocate these address blocks. We have predefined a rule for global unicast address, and that is anything that's going to be used on the internet, the first number, the first hextet, the first 3 bits, the very first number will begin with 001. So we can actually do 001, 0, 0011. So you can actually end up with any number between 2000 and 3000 for our first IPv6 global unicast address. And it's not 3000, it's actually 3 FFFFF. But those are going to be the addresses that are set aside for global unicast addressing, meaning these are going to be the ones that you get on the internet with. So global routing prefixes, you're going to notice how most of them are going to be growing off of fixed lengths. Here, you're going to notice the global routing prefix could be a /48. We add in 16 bits for our subnet, and so this group is 64 bits. You're going to notice it's very common of the first 64 bits being set aside for the network. Subnet ID and interface ID. Again, the subnet ID is used for the organization to identify the subnets that it has. The interface is the equivalent to the host portion, and that's what's going to be manipulated. Nice thing with IPv6 is you can do static configurations for our global address, which is the same thing with IPv4. It's just you can have both an IPv4 and IPv6 address on our interfaces. So how we do this is pretty similar to an IPv4 address. You navigate to the interface, you type IP. This time we're doing version 6, space address, space the actual IP. This time we're allowed to use our slash numbers. With IPv4, we had to do the dotted decimal format. But this one, we could do our slash numbers. If we're looking at configuring a host, same thing, we're going to its network adapter settings, except we're looking at the IPv version 6 properties to configure its IPv address, subnet, and default gateway. The nice thing with IPv6 is we have what's called SLAC, Stateless Address Auto Configuration, meaning no IPv version 6 DHCP, meaning you don't have to have a DHCP server version 6 to hand out IPv6 addresses. The SLAC actually relies on the router advertisement messages to help configure our IPv6 addresses. IPv6 routers forward IPv6 packets, and again, they send the ICMP version 6 RA router advertisement messages. First thing we have to do when we do a router is we have to first of all turn on IPv6 routing. We do that by typing IPv6 unicast routing. That turns on IPv6 routing. Our RA messages can come in a few different options. We could have SLAC only. We could have SLAC and DHCP. We could have DHCP only. So we have some options. The routers that will use to be sending the ICMP version 6 RA messages could also be doing that for just link local addresses. So it's going to depend on how we have it set up. So here is a basic overview. If we are looking at a router solicitation, basically a server comes on, PC says, hey, who's there? The router should then send a router advertisement, and will either go to the DHCP server or the router will assign it the appropriate address depending on what router advertisement options we've set up. SLAC with DHCP, or just DHCP by itself. Again, DHCP version 6, or also known as also known of DHCP for IPv6 or version 6, similar to IPv version 4, automatically receives address information, and again, very similar to IPv4's DHCP. If we're looking at dynamic configuration, meaning we're sending them to our DHCP server, our machine will come on, send an an RS router solicitation to our router. The router should send an RA that says, hey, go to the DHCP server. Here we have our EUI 64-bit process, meaning it's a way for us to put in a 48-bit MAC address so that we can insert an additional 16 bits in the middle and flip a little things so that we could have this to create a interface ID based off of our MAC. A big thing here is within our EUI 64-bit, on the interface side, we take 24 bits of the MAC address, and we take the 7th bit and we reverse it or flip it. So here we have the OUI portion. We split it in half. We add the appropriate FFFE in the center, the 16 bits. We go to the 7th bit, that one right there, and we flip it. So instead of it being a 0, it becomes a 1. And that is our random generated process for our EUI 64-bit process. Examples. Again, you're going to notice the FFFE between the MAC addresses. Notice here our MAC address is FC994775C3E0. There's the last 24 bits. And that means these 24 bits should be right here. Again, we're flipping the 7th bit, which should fall in that category, changing that C to an E. This is part of our randomly generated interface IDs. This will also be based off of the operating system, but it's mainly based off of our MAC address. Going back to our dynamic link local addresses, we have a special one just called a link local address. So after a global unicast address is assigned to an interface, an IPv version 6 enabled device automatically generates a link local one. Again, those are the FE80 ones, so that local traffic can still communicate. Dynamically assigned, again, the beginning is FE80/10. We can actually set them by doing a navigating to the appropriate interface, IPv version 6, FE80, the appropriate address, and then doing link local. Remember, these are going to be based off of a specific LAN. They will not cross a layer 3 barrier, meaning we can have the same address for different networks. So going back to our the static link local addresses, these are going to be specific to those links, never actually leaving whatever network those are on, so that the router doesn't have to worry about routing those over a layer 3 network. So verifying our IPv6 address, we could do a show IP version 6 interface brief that will show us the appropriate information for IPv version 6. We could do a show IPv6 route. Those will show you the routing table. So let's look at assigning IP version 6 multicast addresses. Those are not FE80s, those are FF00/8 addresses. So FF02, those are going to be a multicast address. FF022, again, that's going to be an all-router multicast group. Assuming that we have our IPv version 6 unicast routing turned on. But see, that way you can have an FF02, FF022, and by looking at the last bit, we can see if it's all nodes or all routers. That way we don't have to send them to everyone. Again, FF021, that's all nodes. FF022, that's all routers. So let's look at the soliciting nodes for IPv version 6 for multicast addressing. Again, it's very similar to the typical multicast address in IP version 4 and IP version 6. Here we're looking at the last 24 bits of an IPv version 6 global unicast address to help generate this information. We're looking at the last 24 bits. The remaining bits will remain the same. Alright. So again, this solicited node multicast addressed two parts. We have our multicast prefix, and we have the remaining last 24 bits. Again, because the last 24 bits will remain the same with the appropriate prefix. Let's move on to our verification of connectivity. One of the first ones is ICMP, ping. Well, we can look for, are we able to resolve IPs to address it, or IPs to domain names IP addresses? Can we actually have connectivity via IP addresses? Do we have the appropriate direction and routing and our TTLs, things like that? So all of that can be accomplished with ICMP. Although IP is not a reliable protocol, the overall TCP/IP suite does have things built in for reliability, even if portion of it is not. Again, we have router solicitation, we have router advertisements, we have neighbor solicitations, and neighbor advertisements. So you want to make sure that you remember that there are solicitations. That's the message from our node to our router, and our router advertisement is from our router back to our node. A router solicitation from our node to the router. The router will respond with a router advertisement with the appropriate response depending on how we have it set up. Slack with the HCP, or no Slack with the HCP. We have our neighbor solicitation and our neighbor advertisements, and these are going to be used for address resolution, normally on a LAN. It's also used for duplication address detection, known as DAD. ICMP, using Neighbor Discovery Protocol, that way we can figure out the appropriate address information. And if we're using DAD, we're looking at verifying there are no similar addresses. Ping, if we are looking at pinging ourselves. We can also look at pinging our default gateway and our own address as well. Now remember, we're looking at pinging our addresses, not our remote, or not our gateways. What I mean by that is, first we look at ourselves, then we try to ping our gateway, but we have to be careful that we're looking at usable addresses, things that are in the range, not so much things that are in like the network ID. Here we want to ping this guy over here, so we're going to request it. It's going to go through the router to this guy. This guy should respond or reply back to our recipient. We also have traceroute. Traceroute will allow us to see all the hops between one network and another, up to 30-ish devices down the line. And that's actually all I have for this chapter. I want to thank you.